Hi and welcome to this Leaving Cert Higher Level Maths revision video. In this video we're going to go through revision worksheet 14, which is focused on paper 1 section B. So question 1 is an algebra and functions question worth 50 marks. A company has to design a rectangular box for a new range of jelly beans. The box is to be assembled from a single piece of cardboard cut from a rectangular sheet measuring 31 centimeters by 22 centimeters. The box is to have a capacity volume of 500 centimeters cubed. The net for the box is shown below. The company is going to use the full length and width of the rectangular piece of cardboard. The shaded areas are flaps of width 1 centimeter, which are needed for assembly. The height of the box H is shown on the diagram. So write down the dimensions of the box in centimeters in terms of H. So the first thing we need to do is to understand what we are calling length and what we are calling width. It doesn't matter in terms of the question if you have these the other way around, that's absolutely perfect. I'm going to call this one my length, and then I'm going to call this one here my width. Now, it might be the best maybe to use colour rather than trying to put all of these in, but here are all my H's. So here I have my H's have to, if you can imagine this box being assembled, those two pieces in yellow I've just highlighted, they have to touch each other, so they have to be the same measurement. And the same thing happens here, and here, and here. So they're all my H's. In terms of my length then, so what I've defined as length is this. It's also here, it's here, and it's here. With the rectangular box, the bottom and the top should be mirror images of each other, so they should be identical. So I also have the lengths here. Finally then, I'll have my widths, and my width is going to be here, 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 and here. So that gives me a sense of how to approach the question, because I now have effectively all my sides labelled either L length, W width, or H height. So because I need to write length in terms of H and width in terms of H, I'm going to need equations. So the first one I'm going to work with is the length. Now my length goes across. So if we look at this 31 centimeters here, it's made up of a flap, which I know is 1 centimeter, a green piece, which I know is my length, plus a yellow piece that I know is height, plus another green piece, which is L, plus another yellow piece, which is H, and in total, that should equal 31. And breaking that down, I get 2L plus 2H, take away 1 from both sides, it equals 30. I want to have L in terms of H, so I bring the H across, and I can divide both sides by 2, leaving with 15 minus H. So that gives me my length. Again, if you call that width, that's absolutely fine. We're going to do something similar now for width, but we're going to use the 22. So for that 22, I have a flap, which is 1, plus a yellow piece, which is H, plus a red piece, which is width, plus a yellow piece, which is H, plus another flap, which is 1, and that equals 22. So I'm going to take away the 2 from both sides and tidy up. So I have width plus 2H equals 20, which gives me width equals 20 minus 2H. Now there's no division here because it's just W on its own, so this is simply 20 minus 2H. Now, before I go any further, although you mightn't do this when you approach the question first, it will be good for us to talk about the fact that H has to have values under a given value. So if I look at this length here, if my H was equal to 15, my length will be 0. So for this to work, for this box to exist, H will have to be smaller than 15. If I look at this one, if I subbed in 15 here, I actually end up with a negative width. So actually working with this, if h was equal to 10, I end up with a 0 width. So actually h has to be less than 10, so even smaller than 15. So this is going to be key for our question as we move forward. The fact that in order for this box to exist, for the length and the width to both be positive numbers, we have to have a h value, a height that is less than 10. So it says write down an expression for the capacity of the box in cubic centimeters in terms of h. So my capacity or volume is length by width by height. So for us, that's going to be my length, which is 15 minus h, my width, which is 20 minus 2h, times my height, sorry, I'll do it in bracket, which is times h. So this is 15 minus h. I'm going to multiply my h in here. So I end up with 20h minus 2h squared. I'm then going to split my bracket, 15 times 20h minus 2h squared minus h times 20h minus 2h squared. So that gives me 300h minus 30h squared minus 20h squared plus 2h cubed, which is, if I write it from biggest power to lowest, 2h cubed minus 50h squared plus 300h. So that is our capacity. So part C, show that the value of h that gives a box with a square bottom will give the correct capacity. So remember from the start of this question that the correct capacity, the capacity we want, is 500 centimeters cubed. So if we have a square bottom box, it means that the length is equal to the width. So we have 15 minus h is equal to 20 minus 2h. Bring all my h's to one side, so minus h plus 2h is equal to 20 minus 15. So that's h equals 5. So that is my value of h. And I want to show that it gives the correct capacity. So remember my formula for capacity, I'm just going to call it V for volume. It was 2h cubed minus 50h squared plus 300h. When I sub in my 5 here, I should get 500 if it's correct. So let's see what happens. And into the calculator with this. And we do get 500 centimeters cubed. So we've just shown what they wanted. So QED there. So we've shown that when h is 5, that's what gives me a square bottom, but it also gives me the correct capacity. So part D says find correct to one decimal place the other values of h that give the box of the correct capacity. So let's go back to what we have. We have a capacity formula that is 2h cubed minus 50h squared plus 300h, and we want this capacity equal to 500. What we have here is a cubic. So I'm going to bring over that 500 so that it's equal to 0 so we can work with it. Now, in order to solve a cubic, the same rules apply. It doesn't matter that this is a h instead of an x. We're still going to approach this using our factor theorem. So step 1 is to use trial and error to find a root. So you subbing in values of h until we find one that works. Now, we actually already know a value of h. We already know that h equals 5. And we know that from part C. So this is a root. So in order for us to work and to do long division, we need a factor. So h minus 5 is the factor. So we're going to divide the h minus 5 in. Now you could have used trial and error there, but we already have an answer, so it's going to speed us up to use it. So we're going to divide this in. Our answer is going to be a quadratic, which we're then going to solve for 2 more answers. So h into 2h cubed is 2h squared. 2h squared by 2h squared by h is 2h cubed. 2h squared by minus 5 is minus 10h squared. We then subtract, so take this away. This becomes a plus. When we take away a negative, it becomes positive. We have a minus 40h squared, and we bring down the next piece, plus 300h. So this is minus 40h, gives me minus 40h squared, plus 200h, and this becomes plus when we subtract it, and this becomes minus. So what we end up with here is a 100h, and we bring down our minus 500. H divides into 100h 100 times, and we get 100h minus 500. We want to take these away, and when we do, we end up with no remainder. So our final step then is we need to take this quadratic and solve it. Now, if you want to work like this, that's absolutely fine. We can divide across by 2 just to simplify it a little bit. It just makes the numbers a little bit easier. But if we go back to the question said correct to 1 decimal place. So that implies the factorization won't work, and we have to use minus b. So h is equal to minus 20 plus or minus square root minus 20 squared minus 4 times 1 times 50. Now, if you use the bigger numbers, this would still work. Absolutely no problem. Just what you're subbing in is slightly different, but your final answers will be the same. So when I take the positive version, I get 17.07 or 17.1 corrected to 1 decimal place, and 2.9 centimeters. But what's interesting is the question asked for the other value, implying there was only one. So one of these is valid. Now, a lot of times when we're using the minus b formula or quadratics in general, we end up with like a positive answer and a negative answer, and the negative won't work for this situation. Here we get 2 positive answers. So which one is correct? This brings us back to what we talked about in part A. The fact, in order for this box to exist, given what we have written for length and width, so remember that my length is equal to 15 minus h, and my width is equal to 20 minus 2h. If I was to sub in 17.07 into both of those, I would end up with negative answers. So therefore, the box would not exist, so this is not valid. So my valid answer is going to be 2.9. Just be careful. We're not always going to go back and sub back into the cubic, because both of those answers will be valid for the cubic, because mathematically both of those answers are correct. The problem is, in terms of a real world problem, which is what we're dealing with, they don't work. So often with these real world section B questions, if you want to understand if something is valid or not, you have to go back to kind of nearly the start of the question, or at least where variables like length and width in this case were defined. That way you have a better understanding if the answers are valid or not. So part E says the client is planning a special 10% extra free promotion and needs to increase the capacity of the box by 10%. The company is checking whether or not it can make the new box from a piece of cardboard of the same size as the original one, which was, to remind us, 31 centimeters by 22 centimeters. They draw the graph below to represent the box capacity as a function of h. Use the graph to explain why it's not possible. So this is saying they won't be able to do it. So why is it not possible to make the larger box from such a piece of cardboard? So all they've done is they have actually plotted the function that we had. So let me put up here what the function was. So this was the function we worked out in part B, and it was 2h cubed minus 50h squared plus 300h. Hence the reason it goes through the origin. There's no constant there at the end. So that's the function that they've drawn. And when we're working with it, we were working with 500. So 500 is here. So we would have drawn in a line, and we would have got an answer here. we would have got an answer here. There's my, what we have, 2.9, we had our 5, and then we got this one here, which was about 17.1ish. So that's where we would have got our answer. So now the question is changed, and the capacity, as in there's going to be 10% extra. So if I had 500, which was my original, I'm adding on 10%, which is 50. So my new capacity is 550 centimeters cubed. So if we look at the graph, 550 is here. And when I draw that line in, I only get one answer. My answer here is about 17.2-ish. So the only value of H that will allow us to make a box with a capacity of 550 centimeters cubed is when H is equal to 17.2, and that's centimeters. So why is it not possible? Well, again, go back to what we discussed in part D and again at the start of part A, and H had to be smaller than 10 because after that we got negative lengths and widths. So if we look at the graph here, do you see where it dips below? Where it dips below that axis? That's a big problem for us. So for us, the box is only really valid in this section here. So beyond that, we can pretend like the graph doesn't effectively exist. Mathematically it does, but for the real life it doesn't. Okay, so since 17.2 is bigger than 10, it's not valid. So it's not possible. So that's really what they're looking for. Do you have a sense of what this graph is showing and how it can be used to help us answer the question? So question 2 is an exponential functions question worth 50 marks.
So this question was an exponential functions question. So it was a really good question. It contained a lot of the elements that we see with the exponential questions, including the use of logs. It also then had a little bit of calculus thrown in towards the end, which was, I suppose, it was straightforward and it was nice. So there was a few little parts of this question that were a little bit tricky. So let's work through it now. So Kieran is preparing food for his baby and he must use cooled boiled water. So the equation y is equal to ae to the power of kt describes how boiled water cools. In this equation, t is the time in minutes. So we highlight that. And y is the difference between water temperature and room temperature at time t. A and K are constants. The temperature of the water when it boils is 100 degrees, and then it tells us that room temperature is a constant 23 degrees Celsius. That's important. That caused a lot of confusion for people. So write down a value for the temperature difference y when the water boils and find a value for A. So when the water boils, it's going to be 100 degrees minus the room temperature, 23 degrees, which gives us 77. Okay, so that's our difference. So then to work out A, we go to our equation and say y is equal to ae to the power of kt. So when the water boils, we know that y is 77. We don't know what A is. E then is power K and T. So the time when the water boils is 0. So look at the first bullet point up above. It says T is the time in minutes from when the water is boiled. So when we boil the water, no time has passed. So we get 77 is equal to ae to the power of 0. And remember that anything to the power of 0 is just 1. So we get A is equal to 77. After 5 minutes, the temperature of the water is 88 degrees Celsius. Find a value of K correct to 3 significant figures. So again, we have y is equal to, now instead of A, I have 77, e to the power of kt. So they said here that t is equal to 5, and we want to figure out our y, which is going to be the 88 minus 23. Now be careful, a lot of people, a lot of students at this point took the 88 away from 100. So remember that y is the temperature difference between the current temperature of the water and room temperature. So that gave us 65. So we end up with 65 equals 77 e to the power of k times 5. So we have 65 is equal to 77 e to the power of 5k. Now, we want to get the e, or the exponential part, on its own. So we'll have 65 divided by 77 is equal to e to the power of 5k. Now, can't work it like that, so what we're going to instead use is our log to base e of 65 over 77 is equal to 5k. So what I'll get, I'll just flip this around, 5k is equal to. Now remember that the log to base e is the natural log, so just for ease and for putting it into the calculator, we'll leave it as ln. And to make it as accurate as possible, I would actually leave it as 65 over 77 and then divide my whole answer by 5, and we'll put that straight into the calculator. So when you put that into the calculator as is, we should get minus 0.33888. Now it asks us to round to 3 significant figures. So we have 1, 2, 3 significant figures there, which brings us to minus 0.0339. So significant figures is not the same thing as decimal points. What significant figures means are non-zero numbers. So if a 0 appears before, so at the front or at the end, they're not counted as significant. However, if a 0 appears in between two numbers, then it is considered significant. So we get minus 0.0339 is the value for k, correct 3 significant figures. So Kieran prepares food for his baby when the water is cooled to 50 degrees. How long does it take, correct to the nearest minute, for the water to cool to this temperature? So now our formula is looking a little bit more complete. We have 77 e to the power of minus 0.0339 t. Now we do know our y is going to be 50 minus 23, which gives me 27, and we're trying to work out t. So 27 is equal to 77 e to the power of minus 0.0339 t. Just like in the previous part, we want to get the exponential part on its own. So we get minus 0.0339 t. So I do log to base e of 27 over 77 is equal to minus 0.0339 t. Again, I'm just going to flip it just to make it a bit easier. 339 t is equal to, remember log to base e is ln 77, and to make it easier, I'm just going to put it into my calculator all together. 77, all of this then divided by minus 0.0339, which gives us t is equal to 30.9 minutes, and they want to correct the nearest minute, so my time is equal to 31 minutes. So then it says, using your values for a and k, sketch a curve. F of t is equal to a e to the power of kt between 0 and 100. So this is the function, should actually be equal to a, which is 77, e to the power of minus 0.0339 t. So for just like any function, what we're going to do is create a table with our values. So here's our table. So t goes from 0 to 110s, which we're just following the graph for. We then put it into the function, which is 77 e to the power minus 0.0339 times t. We then work out a value for y. Now, when I've actually created my point, I've left it to whole numbers because it is just a sketch and we won't be able to get a huge amount of accuracy. So every box is 5. So I think once you can get it to the nearest number, you'll be doing really well. So you can see the rounding that's happening there. So now let's put it onto our graph. So your graph should look something like this. So there's my f of t. So I have my points there in blue for 0, 10, 20, 30, 40, 50, 60, 70, 80, 90 and 100. So just again, be aware that we have that nice decreasing exponential shape. And the reason it's a decreasing exponential is because the power is negative. So we have a minus 0.0339 multiplying by time. Time is always positive, so what we'll get is always a negative number there in our power. So on the same diagram, sketch a curve g of t is equal to ae to the power of mt, showing that the water cooling at a faster rate, where a is the value from part A and m is a constant. Label each graph clearly and suggest one possible value for m for the sketch that you've drawn and give a reason for your choice. So this is important because we're now working with this function here. G of t is equal to, now they told me the a was the same, e to the power of mt. Now that means I'm going to start at the 77 point here as well. So let's get rid of all this. So my point is the same point here. And effectively what's going to happen is it's going to come down a lot quicker and it's going to come along and flatten here. So we get something like that. Now, again, a bit shaky because I'm drawing it on the computer. But effectively what you want is any decreasing exponential curve that's sitting in underneath our current function. That implies that it is cooling at a faster rate. So what we want with regard to value then is any m that is less than k will be valid. So remember my k now is minus 0.0339. So for example, you could take your m and say minus 0.05. That's absolutely perfect. So that's the value we can suggest, and it's really about understanding that it's a number that's less than. So and remember that it's already a negative, so the smaller the negative number, it's actually going to look bigger. So it's 0.05, but it's a negative 0.05 there. So when you draw that, just don't forget to label it very clearly, your GT then as well. So it says find the rates of change for the function f of t after 1 minute after 10 minutes. So we have this function f of t, which is 77 e to the power of minus 0.0339 t. Now, when we get a rate of change, we differentiate whatever we have with respect to time, with respect to t. Since this function is already in t, so since t is actually our variable, all we're actually doing here is differentiating f of t. Okay? So we're doing f dash of t, and when you do that, so if you remember your rules of integrating exponentials, and if you don't, they are in your log tables, and we're looking at page 25. So you bring down the power, we still already have 77 e to the power minus 0.0339 t. And that's it. There's no change to the exponential itself. So when we clean that up, we get minus 2.6103 e to the power of minus 0.0339 t. Now, they asked us to do that when t was 1. So we're going to sub in a 1 here. 3 e to the power of minus 0.0339 times 1, which gives us minus 2.52. And they also asked us to do it when t was 10. So for that we get minus 2.6103 e to the power of minus 0.0339 times 10. And that equals minus 1.86. So, very straightforward question there with our rates of change. So what we're talking about is differentiating what we currently have, which was our y, so differentiating our y with respect to t, so dy dt. So differentiating our y, or our function, with respect to time. The last part of this question is show that the rate of change of f of t will always increase over time. Now, so the best way to show about whether it is increasing or decreasing is using our second derivative. So if we use the second derivative, so I'm just again put my first derivative back up here so we have it. Remember that was 2.6103 e to the power of minus 0.0339 times t. And what we do again is we bring down our power minus 0.0339 times minus 2.6103 e to the power of minus 0.0339t. So we differentiate the power and bring it down in front. However, there is no change to the e itself. So what we end up getting here is actually positive 0.088 e to the power of minus 0.0339t. Now, what we would say is this is definitely greater than 0 because t will always be positive, but we have basically got this part here, which is going to be greater than 0 since e is greater than 0, and this part here is also greater than 0. So if I do that multiplied by that, it has to be greater than 0. Therefore, we would say f of t will always increase over time. And that's all they wanted for that part. So very straightforward calculus there at the end. I think just the challenge of the y being the difference rather than a straight number, and I think the fact it was the difference between two temperatures, a lot of students mixed up what they were taking away. But other than that, it was a very, very straightforward question.